Hey guys, welcome to 4.4 Fundamental Theorem of Calculus. In this lesson, we're going to be integrating definitely, and we're going to be computing the exact area under the curves from certain x value to a certain x value. So before we start the lesson, I want to go ahead and just discuss the difference between a definite integral and a indefinite integral. So here's a definite integral. So def. Here's a definite integral. And here's an indefinite integral. Indef. What is the difference between an indefinite integral and a definite integral? The indefinite integral is what we were doing just a few days ago. When you take the antiderivative of f of x, let's suppose the antiderivative of f of x is a capital F. What should always be added next to your solution? It's a plus c. So let's go ahead and just take a look at this. When you integrate indefinitely, in other words, when you don't have an upper or a lower bound, or both, I'm sorry, when you don't have upper and lower bounds, when you integrate indefinitely, you get a function back. This is a function with a constant at the end. That's an indefinite integral. In other words, indefinitely, you get a function, some function. When you integrate definitely, you get a numeric value. And this numeric value represents area under the curve from x equals a to x equals b. So what does it mean to find area under the curve? You guys saw this when you were doing Riemann sums. So here is a function. Here is a function that's raised to the to the fourth power, and we want to find the area from a to b. This shaded region already represents the exact area, but we didn't know how to do this a few weeks ago or a few days ago either. So how do we use to find area under the curve? How do we approximate it? We used rectangular summations. We used Riemann sums. So here's one rectangle, and as you can tell, it's not a very accurate area approximation. Okay? But what would make this more accurate? If we added more rectangles. There's two rectangles. Notice this is my area. My area is increasing because it's getting in more and more accurate. Below here is my true area because of the integral symbol. Integral means the exact area under the curve. As I am adding more and more rectangles, I am getting closer and closer to my exact value. Let me go ahead and add more rectangles at a higher rate. So there's more and more rectangles, and it seems like I am almost there, and then it starts over again because that's what the software limits it to. So the integral, and a definite integral, will just give you an exact area. Now, here's the question. How do we do it? We use what's called the fundamental theorem of calculus. The fundamental theorem of calculus, which will now be referred to as FTC. Make sure that sticks in you guys' head. FTC. The fundamental theorem of calculus says that we can integrate a function, find its antiderivative. So if you notice this f prime, of course the antiderivative of f prime would be an f without the prime. But notice there's no plus c. You don't do plus c anymore in definite integration. Instead, you're going to get the function and you're going to apply the upper bound and then apply the lower bound and then take the difference of the upper and the lower bound plugged into your function. And that is how you find area under the curve. Let's begin with our first example. Example number 1, the integral from 1 to 2 of x squared plus 3 dx. So let's go ahead and integrate as we normally would. What's the integral? What is the antiderivative of x squared? X to the third over 3 plus 3x. And then we're going to go ahead and apply the upper bound and the lower bound and then take the difference. So I like to tell students to write two big parentheses here, because now we're going to apply the upper. If I apply 2 into my x's, I get 2 to the third over 3 plus 3 times 2. You can do this in your head, but a lot of times you'll make a mistake. And then we're going to go and apply the 1. 1 here and 1 here. 1 to the third over 3 plus 3 times 1. And then let's go ahead and compute. So the moment you apply the upper and lower bounds, you're done with the calculus part. Now it all just becomes arithmetic. And this is the part of integration that students suffer the most, is the arithmetic. So 2 to the third is 8 over 3 plus 3 times 2, which is 6. And I like to tell students, distribute already, negative and negative. If I have a positive plus positive, then that means when I distribute my negative, I'm going to have a minus and then a minus another term. 1 to the third is 1/3 plus 3 times 1, which is 3. And I tell my students, just combine whole numbers. 6 take away 3 is a positive 3. An 8/3 take away a 1/3 will leave you with a positive 7/3. And now you can go ahead and make the 3 into a fraction of 3 by multiplying top and bottom by 3, and you get 9 over 3 plus 7 over 3 is equal to 16 over 3. And this represents the true area. You can call it square units, you can call it, I don't know, feet squared, it doesn't matter. You'll never have to answer these in units unless you're doing a free response problem, which will already indicate the units for you, or you may have to just derive the units yourself. But I'll teach you how to do that in the next videos that are to come. Second example. The integral from 1 to 9 of x minus 4 all over the square root of x. Let's begin by first writing this as x minus 4 over x to the positive 1/2. Okay, so integrating a square root is probably a little bit more harder, but if you turn it into a half power, it becomes a little more easier. And you can't integrate this. There's no quotient rule for integration, so what we have to do is we have to divide each term by the denominator. Each term in the numerator is being divided by the denominator now. Dx. And then let's go ahead and divide. What's an x divided by x to the half? You get x to the 1/2 surviving as a numerator. And then a 4 over an x to the half is 4x to the negative 1/2. Now we can go ahead and integrate. The trick to integrating polynomials that have rational powers is you add 1 to the power, so it becomes 3/2, and then you take this power and you flip it to the front as 2/3. And then it's 4x to the positive 1/2 once you add 1, so you flip it to the front as a positive 2, which is 2 over 1. And then we're going to go ahead and apply the upper and lower bounds, so I'm kind of squeezing it in here, so I'm going to do this in red. Upper and lower, x is equal to 1, x is equal to 9. So let's go ahead and do that next space over here. So it's going to be 2/3, 9 to the 3/2 minus 4 times 2 is 8, 9 to the 1/2 minus 2/3 times 1 minus 8 times 1, 2 3/2, and then 1/2 over here. Okay, so let's go ahead and begin with this 9 to the 3/2. A 9 to the 3/2. Here's how you deal with numbers that are being raised to a rational power. You have two options. Option number 1, you can cube the 9 and then take the 1/2 power, which is the square root. Or option number 2, you can square root the 9 and take the cube. Now, a lot of times option number 1 is not going to be the easiest option, because what is 9 cubed? And what the heck is the square root of that 9 cubed? I don't know. But I can take the square root of 9 first, which is 3, and then cube it, which is 27. So this is really just 27 times a 2/3. 3 goes into 27 9 times. 2 times 9 is 18. So the first one is 18. And again, what is 9 to the half? That becomes a 3 times the 8 minus 24 minus and then plus, I'm distributing already, that way I don't get confused. It's going to be minus and a plus. Any number, any 1 raised to any power is always 1. So it's 2/3, and 1 raised to any power is 1 times 8 is 8. Now I can combine 18 and 8 and then take away 24, which is a 2. Take away 2/3, and now I have 4/3 as my answer. So the area under this curve from 1 to 9 is 4/3 square units. Last problem for this video, and then we'll move on. Oh, what happened? Give me a second. Here it is. Okay, sorry about that. So now we're going to go ahead and integrate secant squared x from 0 to pi over 4. Secant squared x seems like a very unfamiliar antiderivative, but if you know your derivatives, you'll know that the derivative of tangent is secant squared. So that means that the antiderivative of tangent, the antiderivative of secant squared is tangent. So this is actually a basic integration formula. The antiderivative of secant squared is tangent x, and then now we apply the upper and the lower bounds. Starting with the upper, tangent of pi over 4 minus tangent of 0. You need to remember your trig, and you need to also remember what does it mean to be a pi over 4. Pi over 4 is 45 degrees, and on the unit circle, pi over 4 is the point square root of 2 over 2 comma square root of 2 over 2 on the unit circle. And you should also know that tangent of any angle is always the y coordinate over the x coordinate. So it's going to be the square root of 2 over 2 divided by the square root of 2 over 2, which you guys already know that that's going to be a 1. Any number divided by itself is 1. And then we also have 0 degrees. So here's 0, the point 0, which is 1 comma 0. And tangent is the y over the x, and 0 over 1 is 0, and that is just 1. And that is the area under the secant squared x curve from 0 to pi over 4.